Hi everyone, welcome back to this second part of the introductory lesson on machine learning. If you've gone through part 1 and you are still here with me, then a hearty congrats to you. Well done for being so persevering. Your perseverance is about to pay off because we are finally going to get to the heart of machine learning. So this lesson is one you will not want to miss. In part 1, I used simple illustrations to slowly acquaint you with how machines use simple functions and regression techniques to predict numerical output values for numerical input data. In practice though, the functions involved in machine learning are much more complex than these simple straight line examples. But even though the functions are more complex and often involve many variables, the concepts remain the same. Because reality is more complex, it is often not feasible or even possible to determine an exact function that will perfectly map known outputs to inputs. So, instead of trying to determine an exact formula, we determine an estimate or approximate function that will do the job just as well. Now you may be thinking to yourself, hang on Erlen, what do you mean by an approximate function? And where are you going with all of this? If you are, I'll clarify in just a bit, but just bear with me because this is at the heart of machine learning. Many times it is possible and in fact very convenient to estimate or approximate a function using a combination of simpler ones. Take a look at these examples. Don't be too intimidated by the math. The key takeaway here is that we can express certain functions as an infinite sum or combination of other simpler ones. And oftentimes in engineering, but especially in machine learning, this is incredibly handy. This ability to approximate functions using a combination of others is exactly what neural networks can do, and you will see how in just a bit. But before we get to that, I want you to first note that there are an infinite number of functions or terms being summed on the right-hand side of these formulae. Each successive term in the sum becomes smaller and smaller, in other words, more negligible. So in practice, we don't need to sum up an infinite number of functions on the right in order to closely approximate the functions on the left. At some point, adding more functions or terms on the right makes a negligible difference to the total sum. At some point we can stop, and the finite sum that we have will be a good enough approximation of the function on the left. But the point is, the more terms you add on the right, the more closely the sum on the right approximates the function on the left. Let's quickly look at two visual examples just to give you a better sense of what this function approximation is all about. Here you can see that we can approximate a digital function or square wave by just combining lots of sine waves, with each sine wave having a different frequency and amplitude. The more sine waves we combine, the better the approximation. Now if you thought math and function approximation is boring, then know that this boring function approximation is the basis for how synthesizers can create the sounds for all that music that you enjoy. It is also the basis for removing noise or applying various audio effects. So there. Here's another visual example. See how this orange graph that starts off as a jagged combination of straight lines eventually starts to approximate the smooth blue curve as more and more straight line components are combined together. Okay, back to machine learning. It is in this context of function approximation that neural networks are so powerful. Please do not be intimidated by this. A neural network is just a powerful way to estimate complex functions by combining many simpler functions together. In fact, you will often see that neural networks are referred to as universal function approximators. Neural networks are typically drawn like this, as a combination of fully or partially connected nodes, creating this network of nodes. Each node is called a neuron, which is why this network of neurons is called a neural network. Each neuron just represents a simple function, and one node or function's output serves as the input to another node. So the net result is a linear combination of simple functions that collectively approximates a function that can optimally map data inputs to outputs. And that's really all there is to it. The more neurons there are in the network, the better the network can approximate some function that accurately represents the relationships between inputs and outputs. But, you may ask, what about visual, categorical, or other non-numerical data types? How do you train a machine that uses all this mathematics we've just been talking about with non-mathematical data like words, colors, or shapes, for example? How would you use a neural network to map non-numerical input such as images to, say, people's faces, animals, or cancerous tissues in CT scans? Well, in these situations, we simply use some clever encoding and decoding tricks to encode visual or categorical data into numerical data, and then to decode numerical data back into visual or categorical data. So, when training a machine with, say, graphical input, we encode this graphical input, whether it is faces, shapes, or text, into numbers. These numbers would be the equivalent of the X input values we talked about in part 1. And we encode the already known outputs, or the equivalent of the Y values from part 1, into numbers as well. And then we go through the same process of creating a mathematical function that optimally fits the input numbers with their known output values. But now we can use a neural network to determine an approximate function instead of trying to derive an exact function. And when we need our AI to recognize new images or shapes, for example, the new image data will be encoded into number format, fed into our approximate function, basically the regression model, and an output will be predicted. However, the output will be a numerical value, which we would then have to decode into the appropriate words or labels that correctly describe the image or other categorical input. Hopefully now you have a better sense of how a machine uses some spectacular mathematical and statistical models as the basis for its rule set to create the appropriate outputs or decisions for every input. Machine learning is all about somehow determining this mathematical model that optimally maps all the inputs in the training data to the correct known outputs. We'll learn more about how a machine does this in the next lesson. Once this model is determined, it can be applied to brand new data input where we don't yet know the outputs. Now, if you still don't have a sense of how the math is involved in the machine learning process, don't worry too much. We will go into slightly more detail in the upcoming lessons, particularly the lesson on deep learning and neural networks. The power of mathematics and neural networks really comes to the fore in the field of deep learning. Now, the house price, insurance premium, and image recognition types of AI that we discussed in part 1 do seem fairly sophisticated, and yet they do not demonstrate the true power of machine learning. These AI programs were trained using the supervised learning method. ChatGPT was also initially trained on large, text-based datasets on a supervised learning basis. But still, as powerful as these systems are, they do not come close to the capabilities that an AI system can develop if it is trained using the reinforcement learning method. In fact, the AI programs that beat the global chess and Go champions were trained using reinforcement learning. Supervised learning would just not cut it for these types of scenarios. And with that, I think that now is the perfect time to start discussing these different machine learning methods. If you stuck with me all the way to the end of this lesson, then well done and congrats. I'll see you in the next lesson.